folks. So last time we were talking about theoretical conversion from A to D and D to A, analog to digital and digital to analog. And so what we want to talk about this time is practical considerations associated with that conversion. And then the next section we'll talk about how to actually implement these in hardware. So when we are converting from a digital input to an analog output, we're going to take a bunch of digital inputs and we're going to run them all together through a latch. And why would we use a latch? We want to get them all synced up together. Remember we talked about gray code. The reason we talked about gray code was we didn't want values to be changing and have an intermittent bad value. So we're going to do the same sort of thing, except we're going to use a latch this time instead of gray code, because the numbers could be anything rather than just changing one up or one down. So we're going to run them all through a latch. We're going to get them all synced up and then push them all together to the D to A converter so that we have the right number at the D to A converter with no intermediates. And then the D to A converter is going to generate that analog output. So we're storing in a register, then we convert. And then once we're converting, then we're going to the D to A converter output is going to hold that value. It's not going to change. It's going to hold that value until the next conversion. And that's what we call a zero order hold. You'll often see it abbreviated as ZOH. It's a zero order hold. We talk about the same concept in digital control because we want to do the same thing. We want to convert a digital controlled value and convert it into analog so that it can operate on a system. And so you'll see ZOH used for D-Day conversions here as well as in digital control classes. But the basic idea is this. If we've got some reference voltage and we've got some number of bits, then we can set up essentially our Q, and then we're going to multiply it by our code, Q being quantization interval. That's what we talked about before. Our code, remember, is going to be all these different binary bits multiplied by 2 to the power of something. And when we put that all together, that's going to give us a binary number, which we've been representing in decimal. But still, it's going to be a binary number that we're going to multiply by our quantization interval, as represented by our reference voltage divided by 2 to the n. So if everything goes perfectly, we're going to get this ideal conversion. And the ideal conversion is going to look like this. Oops, I stepped too far there. We've got just a line at 45 that connects our digital input code. So our code goes 001, 000, 001, 010, 011, and so forth. And these are increasing codes. And essentially, in this case, we're talking about fractions. 0, an eighth, all the way up to 8/8, which would be a full value. So this is something we can scale for 8 different values, which would be 3 bits. We could scale this across anything we wanted. If our reference voltage was 10, we could have 1/8 times 10 volts, and so forth. But in the ideal, what's going to happen is that if we've got all these bits and we have scaled this across to what we think it should be, then as we convert, the actual analog output should track linearly. I mean, that makes perfect sense. If we say it should be 1/8 of the way, then the actual analog output should be 1/8 of the way to full scale output. But that's the ideal. And what actually happens is something different. The actual conversion is going to have a combination of errors. We might have an offset error where everything is shifted up or down by some bit or potentially some smaller value than that if there's something in the chip that you're using. We could have a scale factor where the slope is wrong. So now 1/8 of the digital range corresponds to something less than 1/8, and you can see all the way up here that 7/8 looks like it corresponds almost to 6/8. So the slope is wrong. That's something we could calibrate out, but certainly we don't want to have to calibrate it out. More likely is you're going to have a nonlinearity, and the nonlinearity says, well, it's not going to be straight, and it's not going to be just a change in y-intercept or slope. It's going to be something more complicated than that, something that no longer follows a linear, straight line. And then you could have another type of nonlinearity where it's no longer monotonic. Monotonic meaning that it's always increasing. In this case, it could be increasing and then decreasing and more increasing and then something else. That's non-monotonic. And so that's, again, a nonlinearity. So if we think back to our number line, we're converting this range and now it's in terms of eighths, but remember we could call this 0.0000001. But this is our range in terms of digital codes into something that is going to be typically in terms of volts. It's going to go 0 up to full scale. And remember that this interval here would be our Q. So for analog to digital, same sort of idea. We're going to ideally have this linear relationship, although this one's a bit more stepped because we're going to take, let's see, so right here on our 1/8, 1/4, 3/8, and so forth of our full scale input voltage, we're going to set that to a particular bit. And then we're going to allow that bucket to be 1/2 Q on either side. And so that's where we get this step from. And so the ideal is, again, going to be linear, and then the steps around it. And then in your conversions, you're going to have the same sort of problem. You could have offsets, you could have a scale factor, you could have nonlinearities, and you could have missed codes where the nonlinearity gets too big. And so, again, these first two, you could calibrate. You could calibrate those out if you knew about them. But these last couple are not so good. And so when you want to buy an A to D, what we're going to say is that you generally want to look for what the maximum error is. And the maximum error is probably going to be listed in terms of least significant bits. And so the error, one would hope that the error would be less than one least significant bit, which would mean that you're not going to be off any more than one step. Another fun one is that we might have an input voltage range that doesn't quite match up with our maximum and minimum for our ADC. And so if we've got this blue curve as our input voltage, and we've got minimum and maximum for the ADC like this, maybe it's 0 to 5, maybe it's -5 to 5, whatever. We've got the minimum and the maximum for the ADC, and our blue input curve goes outside of that minimum and maximum. What happens? Well, you know that the maximum gets coded to the maximum code, and the minimum gets coded to the minimum code. Then when you go outside of those bounds, you've lost information. And so these things here get coded to the minimum and the maximum codes respectively, and this information is clipped. This is clipping. So what happens if you go outside your limits? Well, you lose information and you just get the maximum or the minimum values. Now we can fix this a little bit, because remember we could use a diode clamp to make sure that the voltage doesn't exceed it. Again, in that case, we're not getting all the input information, but then we're not damaging our ADC. We're protecting it by making sure that the voltage limits on the input signal are aligned with the voltage limits for the A to D. So that's clipping. Generally, clipping is a bad thing. This is the same sort of thing you see on your oscilloscopes, that you want the input signal to cover as much of the screen as possible without going over. Kind of like The Price is Right. Now, when we actually convert, it's not instantaneous. There's going to be some time delay associated with that. And so we quantify this as the aperture time. So if we have an input signal and it's coming in and we start a conversion, then you would think, okay, this is the value that I want to hold on to. But it doesn't quite happen that way. There's actually a time associated with the conversion, and so it takes a little bit, and eventually we finish the conversion. So that's the start and the finish of the conversion time. And we will note that the voltage has changed by a value of delta V. So this is the value of the voltage changing between the start and the finish of the conversion. And we'll call that conversion time the aperture time. And so ideally we want delta V to be small. We want to say there was very little change associated with this between the start and the finish of the conversion. But how small is small enough? Well, the general rule of thumb here is that we want delta V to be less than 1 Q. Why would that be? If delta V was less than 1 Q, then you know that there's been no more than one least significant bit worth of error. And in fact, if it's less than Q, then you would expect there's been no least significant bits with error. There's been no change. You haven't lost anything. So we can quantify that even by assuming that we've got a sinusoidal signal that uses the full range, and so it's going to have an amplitude of R, which is half of our full range. It's got a frequency of F in terms of hertz. And so we can then say if we want to limit delta V to be less than Q, then delta V is approximately going to be the max slope of the input signal, and the max slope of the sinusoidal input signal will be 2 pi f times r times the time there. So we get maximum slope, and we want to know delta V, and we also have aperture time. So we can um, set that delta V less than Q, and so we get that it's going to be 2R over 2 to the n, that's our Q. And so if we rearrange this, we get that the aperture time must be less than 1 over pi f2 to the n. So we have an inequality that says if you're not going to have any mistakes associated with the aperture time, then you need to relate the frequency the maximum signal frequency, the number of bits, and the aperture time. And so you can look at a particular signal and identify if it's going to be having excessive error. You can decide if the aperture time associated with an ADC is small enough or not, and you can decide if you might need more bits. So we can relate all those. Another thing that we want to look at is sampling and holding, and this gets into aliasing. But if we want to sample, then we need time to convert. We were just saying about that. And so if the signal varies, one way to get away from this is to use a sample and hold circuit. So this would allow us to bypass some concerns about the aperture time. So again, if we want to sample at each one of these points and then hold the value, this would be our zero order hold sort of situation. Except the zero order hold is for digital to analog, so this might be like inverse zero order hold. I'm not sure how you'd connect that, but it's the same sort of idea that we're grabbing and holding on to it. Whereas in the zero order hold, we're taking a value and taking an output value and holding it. So we could do it like this with two followers and a capacitor. And so when we want to sample, we connect these in line, and that's going to charge that capacitor. And then when we want to hold, we'll disconnect. And when we're disconnected here, then the capacitor is sitting there holding a value, a voltage, and providing it to the second follower. And so the capacitor, it's not going to last forever, but it'll sit there and it will hold the value, at least for a little while. So we sample and then we hold, and then we sample and then we hold. But when we're sampling, we're losing that information for what's happening between samples. And so we want to be able to talk about the information that's lost, and whether the information that's lost causes us to misunderstand what's going on. And so this comes from sampling theory. That's the big names in the field are Shannon and Nyquist. And so the general rule of thumb that we get, and this comes from a lot of work in information theory, but the idea is if you can reconstruct a signal, then there's no information loss. Well, we can only reconstruct the signal as long as we have enough data points so that we can always get the frequency components right. Well, we can only get the frequency components right if we have more than 2 samples per period for each frequency component, which means that the sample rate must be faster than twice the highest frequency. Then we'd always have 2 samples per period. If you have less than that, then we have what's called aliasing, and I'll show you some examples of that. Aliasing means that you are going to have the wrong information. Aliasing means that you no longer have the signal that you think you have. Aliasing means that you've done things wrong and you should go back and fix it. So let's look at what that means in terms of some plots. So if I have a sinusoid here, and this sinusoid you can see is at 1 hertz, and so if I sample 20 times per period, then that'd be the second one here. If I sample 20 times per period, then you can see that I get a nice sinusoid. It's stepped, obviously, but it's not too bad. You can see that it's a sinusoid. You can see the amplitude. You can see the frequency. It's great. If you sample 5 times per period, then you can still sort of see that it's got a frequency component, and the frequency component is at 1 hertz. It doesn't look as much like a sinusoid anymore. I mean, if you kind of squint your eyes, you can kind of see the sinusoidal component, but it doesn't look nearly as good anymore. But the key is you still have the frequency. And if you still have the frequency, and you knew it was a sinusoid, well then you could just make it up, and you'd say, well, this is what it should look like. But what happens if you go down to 0.9 samples per time unit here? So if we go down to 0.9, then look what happens. Instead of having that 1 hertz sinusoid. Now, if I kind of squint my eyes and I follow this sinusoid, it's a completely different frequency, which is to say I have the wrong information. There has been information lost in transmission. So this is what we call aliasing. And so aliasing occurs anytime that you sample less than twice as fast as the signal. So you always, always, always want to sample faster. Now, unfortunately, sampling faster means you got to have better hardware, which means it's going to cost more. So you can't always do that. But you must sample at least twice as fast as the highest frequency signal, otherwise you will alias and things will be bad. Now, if you want to do control, for control you generally want to sample 20 times faster. 10 to 20, but 20 would be ideal. And if you get 20, you get this second row. So this is good for control. That way you've got good analog values. If you have anything slower than 10 to 20 times for control, you're going to have some problems in terms of not having some good feedback. But the absolute worst is you can't sample any slower than twice as fast as the signal. If you sample slower than twice as fast, you will not get the right frequency component. So we always sample faster than twice as fast as the highest frequency component of the signal. And then we also want to put in an analog filter to remove signals higher than the sample rate by 2. So we will have our amplifier for our signal, and then we'll have this low pass filter, also called an anti-aliasing filter. That's our anti-aliasing filter. And then our ADC. And a lot of ADCs will have an anti-aliasing filter built in. But if it doesn't, you need to put one in. And the question gets asked, why analog? Why would you need to have an analog anti-aliasing filter? Well, because if you have a digital filter instead of an analog filter, then you can only run the digital filter after the A to D conversion. Well, at that point, you've already aliased, and now you don't know what you're filtering. So you filter first before you alias. And it must be upstream from the sampling device. So here's an example of an anti-aliasing filter. This is an 8th order filter, so this is just a chip that you can buy. So you can put in this filter and look what happens. It's got a little bit of ripple here in the lower frequencies, and then this is the cutoff. That's the cutoff frequency, and above the cutoff frequency it drops really fast. And so if you put in, this is set to 1 kilohertz. So if you put in 2 kilohertz, you can see that you're already down here at negative 80 dB. Well, that's really small. And so this is an example of how we might do an anti-aliasing filter. It's got a steep cutoff, and that comes from the 8th order. This gives us the steep cutoff. Sorry, not the steep cutoff, the steep roll-off. And we will always choose an analog anti-aliasing filter.